Okay, now a couple, just before I jump into this, this new stuff, 12.6, I want to just mention something to you about doing the calculations for volumes, but really mostly for surface areas. I've got a feeling about this. I think that it's easier in the long run to use the formulas instead of, specifically the surface areas, instead of just adding up the surfaces, calculating individual surfaces of a let's say we've got, for example, a hexagonal prism or a hexagonal pyramid on top of a hexagonal prism, some kind of complex shape like that. Instead of just taking all of the triangles and rectangles and hexagons and calculating areas and adding them up, I believe that it ends up being easier to use the big formulas. The formula for lateral area of a prism, we know, is just perimeter times height. The lateral area of a pyramid would be 1/2 PL. Using those kinds of formulas end up requiring you to do fewer calculations and keep track of less stuff. And on those really big objects like that, I'm convinced that it's quite a bit easier. Okay? So just keep that in mind. We'll be in the lab again tomorrow, and I'll, as we're going through problems, I'll feel free to come on up and I'll help you out with them. This is a hard assignment, I know that. I'm well aware that Chapter 12 assignments are really pretty big, and there's a lot of pretty complicated stuff. And I know that. I think they're very important, though. So I'm going to make you do them, but I know they're hard. Okay, surface area and volume of spheres. Let's talk about spheres a little bit. Okay, we know, now we didn't do Chapter 10 in detail. So in Chapter 10, they talked about circles quite a bit. And there's some things about circles I maybe even need to add to that little formula sheet. I never really told you what the circumference or the area of a circle is, maybe. I can't remember. But we need to know that stuff. And mostly you do anyway. But we want to start looking at spheres by taking a second and comparing them to circles. Because what you can think of spheres as being is the three-dimensional equivalent of a circle. Just like a circle is the most symmetric shape on a plane, a sphere is the most symmetric shape in a space, in a three-dimensional space. So in Chapter 10, we would have talked about how a circle is described as a locus of points. Now that's a weird thing here. I'll define that for you. A locus of points in a plane that are a given distance from a point that we would call the center. Okay? What does locus mean? A locus is a fancy math word which just means a set of points that follow some specific directions. Okay? So in this case, we could define a circle as the set of all points that are equidistant, or the same distance away from a fixed point. Now it's easy to draw. For example, if I were to put a tack in the board right there, and let's say I were going to use a little piece of string connected to that tack, and the piece of string had a radius of r. Now, if I wanted to keep the string tight the whole time, and I want to, let's say I've chained a little mouse to this or something, and I want the mouse to move around every place that it can. Yeah, a mouse. Why not a mouse? If he's going to keep that string tight the whole time, so his distance from the tack in the center, call that C for center, is going to stay the same, and he goes every place he can, what would his path look like? A circle. Yeah, he's just going to move around. He's going to keep that leash tight and just move around in a circle. That is, maybe we can lose the mouse part of it, but that is actually our best definition of a circle. It's the set of all points that are equidistant from a common center. Okay? That's a pretty bad looking circle, but you get the idea. Now, what if we relax this definition, or say instead of a mouse now, I don't know how we're going to do this, but I've got this little point frozen in space, and connected to that, instead of a mouse, we've got a hummingbird. So the hummingbird can fly around in 3 dimensions now, right? Meaning, the space of the room. Not like outer space. I mean, just in the space in our room here. if I'm holding this thing in place somehow, and that hummingbird is keeping the string tight, and it's going to fly every place it could fly, what is its path going to look like? Not just a circle, in fact. It's going to look like a sphere, right? Because it doesn't just maybe fly around in a circle like this. It might fly out in this direction also, right? Another way of thinking of that is, what if somehow I had some really fancy kind of newfangled gadget where I could maybe draw in space? Perhaps I'm going to release a little bit of colored smoke as I draw, but this smoke has the special property that it's not going to go anywhere. It's going to stay put, right? If I could draw out of the board like this, keeping the distance the same from the center, and maybe draw behind the board like so, wouldn't you agree that I'm going to end up creating this three-dimensional sphere, right? So really, if we just 3Dify a circle, it turns into a sphere, right? So the properties are very, very similar as a consequence. All right, so what's the anatomy of a sphere look like? Well, we've got, just like a circle, we've got a center at the very middle. We've got a radius that tells us how far it is from the center to the surface, to the edge. And we can talk about things like diameters and chords, and what are they? Well, we would say that a chord is any segment whose endpoints are on the sphere, right? So it's going to travel through the center of the, through the interior part of the sphere, from the surface through the interior to the surface again. And then a diameter would just be any chord that goes all the way through the center, that includes the center, right? So it's going from one edge all the way through the center to the other edge, okay? How's the diameter related to the radius then? The diameter is twice as big, sure, because it's just, two radii stuck together, right? Okay, so what else? That's about all for now on that. Okay, so we have a formula then. I'm just going to give you the formula for the surface area of a sphere with radius r is S equals 4 pi r squared. Now, what's the area of a flat circle? Pi r squared. This is, to me, kind of interesting that it works out that they're related in this way. This doesn't seem, I don't know, I can't see why it is this way. But if I take a circle, let's say I've got a flat basketball that's just sitting in a, it's deflated and sitting in a circle, and I expand this thing up and blow it up, so now it's no longer a circle, but it fills with air and becomes a sphere. If the radius stays the same, what happens to as the basketball stretches out when the air moves into it? What happens to the overall area of the basketball? Well, it increases from just plain pi r squared to 4 pi r squared. It increases by a factor of 4. Weird that it does that, but it does. So that's an easy one to remember because it's just 4 times the size of the area of a circle of the same radius. Okay? All right, now, what happens here when, I'm just going to mention this briefly now, but I'd like to come back to this topic on Friday. Friday before spring break would be a good time. I want to take this idea on Friday, and just to kind of get you thinking about this a little bit. What I want to do is I want to take the same concept I'm going to throw at you right now very briefly and explain why when you watch movies, in all the, it's just over and over again in science fiction movies, if there's something going wrong, a lot of times it's because there are enormous insects that are just wreaking havoc. You see it all the time in movies. Yeah, or maybe it's not insects. Maybe it's Godzilla. It could be Godzilla. It could be King Kong. A lot of times there's a very big, scaled-up version of something that we're used to seeing on a smaller scale, and it's kind of scary because it's not supposed to be that big. Usually it just seems like it's insects, doesn't it? I mean, insects always show up. Okay, it turns out that insects absolutely can't get that big. There's some very simple reasons why it could never happen. Easy to understand. They have to do with this concept. Now, I'll tell you about it briefly on Friday. You'll always know, then I'll ruin all these movies for you because you'll know how fakey they are. You just simply can't get an amp that's that tall. It would never, ever work. Very simple reasons. So just to kind of get us thinking about that, we'll refer back to this on Friday, and this will kind of jumpstart our talk on Friday. What happens to the surface area of a sphere if I double the radius? So let's say I start off with a sphere of radius 2 inches, and I end up with a sphere of radius 4 inches. What happened to its surface area? easy calculation. We have the formula, right? Seems like it ought to double probably, right? Well, if I plug in 2 in for the radius in my surface area equation formula, I get 4 pi times 2 squared. Well, that's 4, right? 4 times pi times 4 is 16 pi. No big deal. 16 pi square inches would be the surface area of that sphere. If instead I take a sphere with a radius of twice that big, I've doubled the radius to 4 inches. If I plug 4 in for r, I get 4 times pi times 4 squared, which is 16, of course. 16 times 4 is 64. So I get 64 pi square inches. Well, how much bigger is 64 pi than 16 pi? 4 times. So hold on here. I doubled the radius, but the surface area quadrupled. Okay? So that's an important concept, that when we deal with shapes that aren't flat, well, even flat shapes, things like this can happen. Just because I double one dimension doesn't mean that all the other dimensions necessarily, all the other measurements are going to double with it. Things can be non-linear, right? They can grow at different rates, as they did here. Okay, and we'll look more at that on Friday. Okay, a little more anatomy of a sphere. Hey, in the back, quiet. If I cut through a sphere with a flat plane, like let's say I'm cutting through a spherical apple with a knife. It's a perfect sphere. If I cut near the top, I'm just going to create a cut that's a small circle, right? But every cut I make is going to be a circle if I cut through a sphere. Now, the biggest circle I could make is called the great circle, and that would be the one if I cut right through the center, right? If I made a cut through this sphere that included the absolute center of the sphere, then what could you tell me about the 2 pieces that I cut off of this thing if I cut it right down the middle? They're equal, right? They're exactly the same in every way. They're congruent. And what we call those are hemispheres. Hemi just means half. So those are half spheres. Anytime I cut through a great circle, I separate the circle into 2 identical hemispheres. Okay? All right, so down to the nitty-gritty here. This is the kind of stuff you're going to do in the assignment. What if we know, for example, that the circumference of a great circle, cutting through a sphere right through its center, the circumference of that great circle, and therefore the circumference of the whole sphere, right, of like the equator on the sphere, is 13.8 pi feet. Okay? Could we find the surface area of that sphere? Yeah, we could. How? What do you think? How could we do that? What do you think? If I look at the formula for surface area, what does it depend on? Here, I can go back a little bit. The formula for surface area, yeah, 4 pi r squared, right? So in order for me to calculate a surface area, I really need the radius, don't I? Right? But if I'm given the circumference, even though I'm not given the radius directly, I could calculate it, right? Because I know that circumference of a circle is what? Pi times the diameter, or another way of saying it is 2 pi r. Good, okay? 2 pi r. So if I know that the circumference in this case was, what was it, 13.8 pi? If I just set 13.8 pi equal to 2 pi r, I can solve for that r, get it by itself, by dividing both sides by 2 pi. And then what happens if I divide pi by pi? Yeah, it's 1, so it cancels. So I just get 13.8 over 2, which is 6.9. So r, in this case, the radius of that circle, or that sphere, is 6.9, I think it was. All I have to do now is plug that into the surface area formula, feed it into that formula, and I get 4 times pi times 6.9 squared, which just gives me a number, 190.44 pi square feet. There's the surface area. Okay, no big deal. Right? All right. This is what I really want to show you. This, to me, in kind of a mathy, kind of nerdy way, this is really pretty cool stuff. And I want you to give this a try, really. To me, this is, as a calculus teacher, this is something that I'm just amazed that we're able to do this. We're able to add up we're able to come up with a correct formula for the surface, or excuse me, the volume of a sphere based on only the stuff I've already told you. We have to be kind of tricky about it. This is a very good example of how we can be clever in the way that we look at a sphere. We can cut it into pieces that make sense and add up the volumes of those pieces to get the volume of the whole. Let's put that away. Okay, so let's say we take this, pretend it's a perfectly spherical apple again. Okay, a pretty rare thing, but we've got one here now. If I want to find the volume of that apple, I could cut that apple into a bunch of small pieces. Now imagine I'm going to do this. I'm going to make some vertical cuts. Each cut has to go through the center, okay? And I'm going to make some kind of horizontal cuts, sideways cuts. If I do that a whole bunch of times, wouldn't you agree that the pieces I'm going to cut are going to look like that? If all the cuts on the surface were vertical and horizontal, I'm going to get square profiles on those, right? And if I were to pull one of those out, it's going to look like a pyramid, right? It's got a square base, and then it's going to taper to a point at the exact center. Now, one thing though, is this exactly a pyramid? What's different about it? It's very much like a pyramid, but there's one thing that's a little bit different. What do you think? The base is going to have a little bit of curvature to it. It's not going to be flat like a pyramid. If I pick this thing up and set it down, it's going to wobble a little bit, isn't it? Because the surface of the apple, of course, is curved, right? But if I make these pieces really small, would you agree that that curvature is not very obvious? And that's an important concept in math. In fact, it's something that, well, here's a good way to illustrate it. Anytime that we look at a large object, if we look at a very small piece of a large object, the overall characteristics of the large object can tend to disappear. For example, the Earth. For much of human history, people had no idea the Earth was a sphere. I mean, in fact, there was a time not that terribly long ago when if you had said that the Earth was a sphere, people would have laughed at you at best and might have burned you for being a witch or a wizard or something weird like that. It's a worst case scenario. Wouldn't have been good though. People, that did not coincide with what people in places of power were telling everybody. The Earth was pretty obviously flat. Just look around, and you see it's flat. If you go out on a boat on a calm ocean, it looks darn flat if you're down that close to the water. But of course, we know better than that. If you even go up in a plane really high, you could start to kind of get a little bit of a sense of the curvature. And if you go to the moon, well, the Earth is, you could just hold up your thumb and block out the Earth. So it's obviously very curved. You can see the whole planet. And it's a sphere. It's not a perfect sphere, but pretty close. So how smooth is the Earth, by the way? It's got it's pretty bumpy, lots of mountains, right? Do you know that if you compare the Earth to a billiard ball is rougher than the Earth? If you were to scale the Earth down to the size of a billiard ball or a billiard ball up to the size of the Earth, the billiard ball would be considerably more mountainous and rougher than the Earth. How about that? What's that? Like a pool ball. So even though the mountains look pretty big to us, and there's parts of the Earth that look pretty rough, that's just because we're so small and it's so big. If you go out to space, it looks very, very smooth. Okay? So my point being that if you get very near the surface, the Earth looks awfully flat. Just like if we take very small pieces of this apple so that these squares are really tiny, it's going to look an awful lot like a pyramid. Never perfect, but awfully close, right? Okay, so then now we know how to deal with a pyramid. What is the formula for the volume of a regular pyramid? Remember? Say 1/3, I heard, times the volume of the prism that we carved the pyramid from, right? So 1/3 the base area times the height of the pyramid, right? Now here's our pyramid. We're going to call the base area in this case B. Okay, we won't measure. We just know it's B. And the height of this pyramid, isn't that just going to be the distance from the skin of the apple to the exact center? What's our name for that distance, by the way? Radius. Yeah. So our volume then of each of those pyramids that we're cutting into this apple is just 1/3 times b, that area of that little square, times the radius of the apple, right? Radius of the sphere. Agreed?
Agreed.
Okay. How many of those are we cutting? Well, we're making them small, so we're not even going to keep track. We're cutting a lot of them. To keep track of them, we're going to call that number n. It's so big, we don't want to count. Too big. Okay. All right. You with me so far? Make sense? All right. So now here's what we can do. Here's the beauty of the mathematics here. We can turn this into a formula pretty easily. We already know what the surface area of the sphere is. The apple's a perfect sphere after all. I told you, surface area of a sphere is what again? 4 pi r squared. Very good. So we know the whole apple, the entire skin of the apple, has to have a surface of 4 pi r squared. That's the area, right? Now, if I were to add up all of those little pieces that I cut out, if I reassemble them, they make the apple. Agreed? That's what the apple's composed of, is all these little pyramids that we're going to stick together, right? Everybody okay with that? All right, so let's add them up. Each one of those little pyramids has a volume of 1/3 the base, the area, surface area of that little pyramid, times the radius of the apple. That's the height of the pyramid. And I have n of those total. So if I multiply the volume of one of those times n, which is the number of pieces, I should get the whole volume of the apple, correct? Okay? One nice thing about math is we're able to do algebra. We're able to move things, we can follow certain rules and make things look the way we want them to look. Bigot, put that away, please.
What?
So if I've got these things I'm multiplying together, I've got 1, 2, 3, 4 things being multiplied together. When I multiply stuff together, I don't have to multiply in any specific order. Multiplication is both commutative and associative, so I can decide what the order is I'm going to multiply these things in. Well, let's do this. Let's take the n and move it over here. Let's move it over next to the b. So now I've got 1/3 times n times b times r, and I can choose the order in which I multiply these 4 things together, because I can only multiply things 2 at a time. Let's multiply the n times b first. Now, b was the area, remember, if I go back one slide, b was that little area, that little itty-bitty area of the pyramidal piece of apple that I pulled out. That's b. I have n total pieces. So if I take that little green area times the number of pieces, what should it add up to? 4 pi r squared. It's going to add up to the whole surface of the apple. I guess it's a green apple this time, right? There's the little piece of green skin. That's one of the pieces. If I add all n of them together, I'm putting the whole apple back together, and I've got the whole green surface of that green apple, right? Everybody agree? Okay, so then n times b is just 4 pi r squared. That is the surface area of the whole apple, right? So this becomes, here we go. So this becomes that, right? Well, that's just the surface area. Now, if I just simplify that, 1/3 times 4 is 4/3 times pi times r squared times r. Well, r squared times r is just r cubed, right? So look what I get. I get the formula volume equals 4/3 times pi times r cubed, and that is exactly the volume of a sphere. Okay. How about that? That's pretty amazing to me. Isn't that cool how we can do that? That's the formula. That's it. Literally, all adds up to our apple. Okay? All right. Last example. I think this is kind of interesting too. Now, this is the way ball bearings are really made. Ball bearings are a big deal. Anything that turns on a wheel has ball bearings, and it has a bearing with a bunch of little balls in there that rotate around, and that's how you put grease in there, and that's how the thing turns. So they're big. I mean, they're hugely important to anything that needs to rotate on an axis. All right, so ball bearings made of steel. How do we make them? What you do is you create this long cylinder of steel, and then you literally just go in and cut that thing in little pieces to create the slugs. You heat them up so they get kind of soft, and then you put them in this hydraulic press, which just literally molds them into the shape of a sphere by putting tremendous pressure. But this turns into that. That's how it works. So if we wanted to create ball bearings of a certain size, a certain radius, that's just going to depend on the volume of the slug that we start with, right? Because what's the one thing that's going to be the same between the before and after versions of that hunk of steel? Maybe not the same radius. We don't necessarily have to have the same radius or the same diameter. Would the surface area be the same? No, it wouldn't, would it? Now, I'll give you an example of why it clearly wouldn't. What if instead of this being a nice cylinder, what if this were squashed down into a big flat pan? It'd have a lot of surface area, wouldn't it? Right? But the same amount of steel. And so clearly the surface area could change from the cylinder to the flat pan to the ball bearing, right? To the sphere. So the surface area could change. So could the radius. But what would have to stay the same? Volume. Yeah, because the volume is literally the amount of stuff. That's the amount of steel, isn't it? So the volume would have to be the same from here to here. We're just going to reform it as all, right? So if we wanted to find out, let's say we started with a slug that was 1 centimeter in radius and 2 centimeters in height, the cylinder, and we wanted to figure out, well, when I turn that into a sphere, what's the radius going to be? Could I do that? Seems like I could, doesn't it? Couldn't I calculate this volume pretty easily? I know the formula for the volume of a cylinder. If I knew the volume, all I'd have to do is figure out what's the sphere, what radius of sphere would fit that volume using the formula that we just created, right? Well, what is the formula for the volume of a cylinder? Anybody remember? What is that? What's the formula for the volume of this cylinder? Pi r squared, h. Yeah, just the area of the base times the height, right? Circular base, pi r squared, height of 2. So if I plug that stuff in, pi r squared times h, plug in my details, 1 for r and 2 for h, I get 2 times pi in volume, in cubic units, cubic centimeters, let's say. Okay, so 2 cubic centimeters. To find the radius of the ball bearing that would fit, then I'm just going to set that volume equal to 4/3 pi r cubed, the volume of a sphere, and solve for r, right? That's what algebra does for us. So if I solve for r, what are the things I have to do to get that r by itself? What would I do? And I don't really like the way they do this. Let's do it differently. So we've got 2 pi equals 4/3 pi r cubed. Anytime I have a variable by itself I can point to, I can isolate it, right, from yesterday. So how do I get that r by itself? What do I do first? Yeah, I could divide by 4/3, but even better, let's multiply by the reciprocal. So if I multiply each side by 3/4, and really that's just 2 over 1, isn't it? Okay. Then the 3's cancel and the 4 cancels. That's good. So I just get pi r cubed. On this side, let's see, I get 6 over 4, which reduces to what? 3 over 2. So I'm going to get 3/2 pi equals pi r cubed. What else do I have to do? Divide by pi. If I divide both sides by pi, that's just canceling them out algebraically, right? I'm going to get pi over pi, and they'll cancel. And then the last step, this tricky one. What do I do to undo an r cubed? Cube root. Now, cube root both sides. So I end up with r equals the cube root of 3/2 is my exact answer. Now, if I want to turn that into a decimal, well, we can do that. If I turn it into a decimal, I get about 1.14 centimeters. So that's the radius of the ball bearing we get out of this. Okay? Make sense? Sort of, kind of, maybe? Okay, we're out here at 105, right? Okay. Well, okay, I'll tell you what I'll do. Being as we're ahead a little bit, doesn't make sense to go to the lab because we're getting pretty close to the end. Here's why. I'll give you real quick. I'll give you why it is that insects can't get huge. Here's why they can't. If you look at say an ant. Here's my ant. Okay, this is going to be a red ant. So I've got these feet on the ant, and then these legs that go up to the ant body. And here's my ant body. It's got a bunch of legs. Let's focus on one of those legs. That's my ant. Right. Okay, and it's got some legs, but we're just going to focus on one of them. How many legs does an ant have? Six legs? Six, right? I think six. So anyway, here's my ants. 3 legs on one side, 3 on the other. If we look at the legs that support that ant, anything that's got structure, that has strength to it, the strength of the supporting strength of any material, doesn't matter if it's the keratin in the exoskeleton of an ant, or if it's steel or wood or whatever, the strength is based on, it's proportional to, we'd say in math, but it's based on the cross-sectional area of the thing that's providing the structure. So if I were to take one of these legs and let's magnify it, and I cut a cross-section through it, it depends on how big that cross-section is. In order for me to double the strength of an ant's leg, I would have to double the cross-sectional area of the ant. Does that make sense? Of the leg. You have to have twice as much area in the cut to be twice as strong. That's the way physics works. Okay, now let's say we take an ant and we're going to scale it up. See, ants are about that big, so if I want to scale it up to something really scary looking, I probably need to maybe increase it by a factor of, let's say, 200. Okay, that's going to give us an ant that's, yay big, pretty scary looking, right? What's that going to do? Now, if I increase, let's take a look here for just a second at our spheres, because most of the ant looks pretty spherical, doesn't it? And it doesn't even matter if it's a sphere, by the way. It could be anything. It could be a sphere or a cube or a cylinder. All shapes work the same in this sense. Let's just treat it like a sphere for now, though. If I compare the measurements, okay, if I want to look at the radius of the leg, and if I double the size of the ant, I'm doubling the radius of its leg, right, the cross-section. Everything is going to double on the ant, all the linear measurements. Okay, let me go back for just a quick second here. So if I go back to here, does everybody buy this? That if I make the ant twice as big, then its leg is going to get twice as wide, and so the radius is going to be twice as big? Okay. Now, what's going to happen to the cross-sectional area? If I double the size of the ant, the area of that circle, which is pi r squared, is going to increase by how much? If I double the radius, it's going to increase by 2 squared, or 4 times, right? Does that make sense? So if I increase the ant by a factor of 200, then 200 squared is 40,000. Okay. So I'm increasing the radius of the leg. I'm increasing the area of the cross-sectional area of the leg by a factor of 40,000. That means it's getting 40,000 times stronger. It can support 40,000 times more mass. Okay, but here's the problem. If I look at a sphere, if I look at a three-dimensional shape, the volume equals 4/3 times pi r cubed, right? So if I'm increasing the radius of this ant, increasing all the measurements by a factor of 2, what's 2 cubed? 8. So then everything is increasing, the volume is increasing by a factor of 8. And what's going to tell us how much the ant actually weighs? Its surface area or its volume? The volume, right?
What about its density?
Okay, but we'll assume that the ant's density, it's made of the same stuff, so it's going to increase just normally, right? If I double the volume, the density stays the same, so I'll double the mass, right? So then if I increase the volume of this thing now, if it's blowing up at a scale of 200 times bigger than it was, now I've got to cube 200, and hang on. And now I get an answer of 8. I get the answer of 8 million. So you see the problem there? Yeah. You get to a certain point where, and this is, you got to know this about science fiction movies. You get to a point where the weight of the ant just increased by a factor of 8 million, but its ability to support itself only increased by a factor of 40,000. In fact, you could say that the weight is growing 200 times faster than the strength, the supporting strength. And so you get to a point pretty quickly where the ant just can't support itself anymore. It's too big. In fact, that's why you can't build, people talk about building a building that goes 10 miles high. It can't be done. Probably. Because you'd have to have the base of the building be miles across, and that wouldn't make any sense. Right? You just can't build, you can't scale things up indefinitely because the volume always is going to increase much faster than the cross-sectional area, right? So you couldn't even have King Kong. It couldn't support itself. Its legs would have to be, it'd have to look really out of proportion. And if you look at dinosaurs, what do they look like? If you look at pictures of dinosaurs, they're mostly leg, right? You got a dinosaur and it's got these huge legs supporting this pretty small body and a great big mouth, right? But the legs are enormous because it weighs so much. It's a pretty bad dinosaur, but you get the idea, right? Here's this little
It's got the tail.
Oh, tail, yeah. There you go. Now, there's my dinosaur. How about that? Yeah. I never claimed to be an artist.